Okay, it's almost time to start. Can everybody out there hear me? Anybody hear me?
Yeah.
Okay, all right. Then stop me if you have a question. We're going to follow our usual procedure to whatever degree we can. First thing on the agenda, if I remember correctly, I was going to let you know that if you had some questions about this homework number 5 on the Roth criteria, we can take out some time and try to address those questions if you've got them.
Can you go ahead and record again? It's still not letting us.
You know, he was here, he said whatever he did, I thought it would let you do it. I'm doing the cloud recording again.
Oh, okay.
So until I figure out how to do it, I'm gonna just keep doing the cloud recording.
All right, thanks.
Any other questions? Okay, so just so you know, I don't have that quiz ready yet. I'll post it on Friday, and you'll have the weekend, and you can. There'll be like a deadline, like Monday or the following Monday to turn in. It's the format will be similar to other quizzes. The intent is not to be comprehensive. The intent is, okay, if you study the homework, then this sample question would be something you should be able to handle, or homework and also class examples. So, you know, it's always a mistake to assume that the quizzes are 100% representative of the material covered, but they're a sample. So just so you know how that would probably go. Anyway, any questions on that policy? All right. Since I'm not hearing any questions on that, let me follow up with one other point that was raised last time about time outside regular class for questions. I posted this notice as an announcement on our class. So I'm thinking this would work reasonably. On Mondays and Wednesdays, I would automatically keep the Zoom open for 15 more minutes. If I don't get any interruption in there or no one has any questions, to me it'd be a sign that there's no need for questions at that time, and I'll probably just shut down. And then if someone has questions, I'm more than happy to go as much as an hour or more if necessary. But the point is, if no one asks a question or no one jumps in for the next 15 minutes, starting around 12:15 on Mondays and Wednesdays, then don't expect to find me at 12:45. I mean, 12:30, I'll probably just shut it down and go home. Now, Friday is also open. However, with one exception, on Fridays, if you want me to keep it open, you have to tell me. That's all. It won't be automatic. But I'm willing to be here for, like I said, another hour afterwards, up to an hour, if there's still questions out there to be handled. Any questions on that plan? Okay, I'm not hearing any questions on that. Okay, so the next thing, according to my notes, we did finish last time the material for what I believe would be homework 6A, and that's associated with the performance measures stuff, and that's already been, the key has already been posted. Just to let you know, if you want to start looking at that anytime, it's there. But so today we're going to start on the follow-up topic in chapter 5 called Steady State Error of Feedback Control Systems. All right. Okay. The figure at the top is the starting figure for this section. And if you look at it, you can immediately tell that, in fact, the correct choice for the feedback transfer function is simply 1, because it's, as shown, there is no specific block appearing there. As a disclaimer, you know, at the end, we'll cover some cases where the feedback transfer function is not unity, and then leave it at that. But for right now, the primary focus would be on problems centered around this diagram. Any questions so far? Okay. Now, I'm just going to claim by inspection from the rules we've had before for so-called the canonical form, when you have this feedback, this typical feedback loop here, would suggest this is the you know, the so-called capital G over 1 plus GH, but this whole thing at the top serves as the G. And so that would be the transfer function, Y of S over R of S. The whole section is about a topic called tracking error, okay, and which we can define somewhat reasonably as the difference between the output, or the input minus the output. And we know from the definition of the transfer function, we can write the Y of S that way. So if we plug that up into there, from 3 into 2, we see that, in fact, that gives us the opportunity to factor out the input R of S and rewrite the tracking error this way. You can see that if you, since the T of S is up here at the top, but there is a factor of R there, it can be factored out. And then, of course, that minus sign there comes back here. Now, for where we need to go, it is in our best interest to simplify the form a little bit, which can be done, because notice that there's 2 terms there. They can be put over a common denominator, and appropriately, some simplification can be done. And so when you put over a common denominator, the first thing that happens, it looks like this. But of course, if you observe the numerator, you see there's some cancellation possible. And of course, when there's a possibility, we often follow it. So we're going to let that cancellation go forward, and you get this result. Now, to be a little more specific, the focus is mostly on what would be called the steady state tracking error. And we can use the final value theorem to help us go in that direction. Now, you could say, well, you know, what is the E of t here? Well, using our conventions that we are most familiar with, you would say, well, that's the lowercase symbol represents what's happening in time, and the uppercase symbol is pretty much the Laplace S domain version of that same signal. So we would argue, and even though it's not specifically in the notes, we would argue there is a connection between the capital E of S and the lowercase e of t. They're related, as you might guess, by the inverse Laplace. If you can take you're taking the Laplace of the lowercase e of t gives you the capital E of s, or vice versa, doing the inverse Laplace going the other way. That being the case, then we can see that, well, by definition, this time domain error signal is the counterpart to the S domain signal. Here we have the R of S minus the Y of S all in the S domain. And here we have the counterpart of the time domain signal for the input and the time domain signal for the output. And that difference, according to that same kind of rule, becomes what they call a time domain tracking error. Now, we haven't really used a final value theorem, but it's coming, as you would guess, based on the page. You know, all we really know, we do know that we can get the final value of the signal if we know the Laplace transform and then multiply by S and then take the limit that S goes to 0. So that's consistent with the final value theorem. Not hearing any questions. No questions out there?
No questions.
Okay. Okay, then I'm going to keep going. All right, so to make progress on this in the direction that is commonly done in control theory, we need to assume a form, mathematical form, for the so-called, I mean, some people might be tempted and would be not incorrect, call it the control block, and then this would be often called the plant block. But anyway, it appears, as you can see, those as a product of transfer functions. So the form that we assume is, well, we can always write these as essentially a ratio of polynomials for the numerator and denominator. And presumably we're allowing the fact that there could be cases where it's not identifiable as a, how should I put it? Every factor, when factored, could in fact have, or at least in most cases, would in fact have a non-zero root, and that would apply to both the numerator and the denominator. But also, we want to allow the fact that there could be factors of s in the denominator, and that's left as s to the n. And to account for other factors that could be there, sometimes it's just the control block could simply be a constant. To allow for constants, we have a k there. All right. So what you'll find in practically all these problems, the GCGS quantity is identified. So that's what you kind of keep in mind when it comes to problem solving. Often the question is, what is given information, usually in a problem? And for where we're going, the given information would be typically be the transfer functions that are here. Okay, so you can quickly take a product. Now, sort of as a motivating factor to kind of put this in perspective, this S over N, I'm going to remind you that in control theory, we often have controllers that involve elements which, for example, is proportional, which, like, for example, just a constant. Integral would be multiplied by S, divide by S, and derivative be multiplied by S controllers. So basically you could have a constant. The integral would be the 1 over S, and the derivative would be multiplication by S. Okay, so basically you could have those factors that are involved in the control process. And so you can imagine the 1 over S factors look a lot like pretty much integral factors. Now, the ZI and the PI, of course, are connected to the zeros and the poles, but not directly, in the sense that they're not exactly the same. And what do I mean by that? What I mean by that is that the actual zero and the actual pole is not the ZI and the PK, but is in fact the minus of that. All right. Now, I would argue the following. Now, that might have been a choice that is typically used in controls, and I would contend I've seen it more places than one. So you just need to realize that in this context, what that would mean. Now, you could say, well, why is it minus? Well, if you set the S plus ZI equal to 0, the root to that would be S equal to a minus ZI. So that tells you that's the actual 0 is the negative of the ZI, and the actual pole is the negative of the PK. Just to clarify a point. So we see that in the expression there's this S to the N. Now that N will play an important role in the discussion of this section from the chapter, and in fact, to the degree that we actually give systems a label based on that N. In other words, if the N is 0, it's a type 0 system. If the N is 1, it's a type 1 system, etc. Okay, so it's not a terribly complicated connection, but it's one that is made in the section. So the system, in this sense, from the tracking viewpoint, is identified or connected to this so-called type label, all right, which is controlled by the N, which has to be greater than or equal to 0. Can be 0, in which case would be a type 0 system, etc. Now, what we'll see is that in fact the type of the system will have a lot to do to how well it can track the input, and we'll be more specific about what it means to track or not to track. Okay, any questions so far? Now we do allow the factors, even up in the numerator and the denominator, to be complex. But as we know, when you have one complex root, you've got to have another one, so that when you multiply the two factors together, you essentially end up with the two factors. You end up with a quadratic with real coefficients. All right, well, I'm at the bottom of the second page. Any questions? Comments, questions? Hello, anybody else?
No, sir.
You have a question? No questions?
No, sir.
Okay, well then I guess I'll keep going. All right. Now, so in this business of tracking, as we can see, as we've already seen, we can put a label on a system in terms of type based strictly on this this S to the N that appears out front. And the N identifies the type. Now, the The issue on the tracking can be viewed in the following way. There are certain test signals that we can put in to see how well the system can track. So all our analysis, and maybe that's a good thing in a way because it limits it, all of our analysis is tied to certain specific time domain signals, okay? For which you could say we're testing the tracking capability of the system with these inputs. And all of the inputs, all the test input signals that we're interested in will follow, at least in the S domain, this mathematical form, A over S to the M. Now, what that really means is we're going to need to remind ourselves of from the Laplace transform table, that this rule, which essentially connects what's happening in the S domain to the time domain for this particular form in the S domain. And I would argue, if you look at 8, you can see, well, there's no S minus something up here because it's just the way it appears. So the correct value for A should be 0 if your objective is to get the time domain for that, that input, which we want to. And you could argue then, we would say, well, then the M here could be interpreted as, and not incorrectly, interpreted as n plus 1, right? Because there's an n plus 1 there, there's an M there. If we set the M equal to n plus 1, then the n we need will be m minus 1, right? If you solve for the n from that algebraically, it's n equal to m minus 1. So, so let's do a short example on that. So of the 3 test signals that we're going to be looking at, one of them would correspond to what's called the parabolic case or parabola case, m equal to 3. And you say, well, why, with that m, you may not automatically know why it's called a parabola, but we'll see in a minute. So if we take m equal to 3 and a equal to 0 up here, right? So if m is equal to 3, then the n is m minus, so that's n plus 1 is equal to 3. So n is equal to 2, right? If m is 3, n is 2. That 2 goes up in there. The a is set to 0. And tell me if you don't, so basically we're arguing that if we start from here with m equal to 3, we end up there. Now this is the right time to ask a question if you got it. And yes, we see now why it's called a parabola, because of that t squared dependence. Not hearing a question, so I have one for you. If m were equal to 4, what kind of time dependence might I expect? Any
Raised to 3.
Excuse me?
Raised to 3. T
Yes,
cubed.
correct. T cubed, cubic, correct. Correct. Okay, so since I'm not hearing a question, I'm gonna keep going. All right. So the 3 cases, input cases that were, oh wait, back up a minute. No, this is not about the inputs. Okay, what we're going to find out is the following: that when it comes to evaluating the possible errors that we can get, remember the steady state errors, that's ESS. When it comes to evaluating the steady state error, every case that we get will boil down to, or every problem we look at will boil down to 3 cases. And those 3 cases would pretty much can be described in the following way. And there's no surprises intended here, so if you have a question, bring it up. If the steady state error is 0, that's considered the best case in terms of tracking, because that means your output and your input are exactly in the steady state limit become the same. And so there's perfect tracking if the steady state error is 0. Now, so that's one case. Now we're going to find that there's there's an in-between case, which is if the steady state error is finite. Okay, in other words, it doesn't blow up, but it's not 0. And the third case is it blows up. So as you might guess, the third case is always unacceptable in terms of if your interest is for tracking, which in controls it usually almost always is. The in-between case is quite often acceptable. Okay, so when I put the sometimes there, it may depend on the size of the error, but usually in those situations, you can adjust some parameter to reduce that finite error. But no matter what, okay, it's going to be finite. Now I'm maybe getting a little ahead because we haven't actually seen how this is going to come out, but I'm just warning you in advance. That's what's going to happen. And so let's see, the last thing on the page, which you can check for yourself, I'll leave it as a good exercise, is if you take the, just like we did up here at the top, use the same kind of logic. If you take the cases for m equal to 1, m equal to 2, and m equal to 3, we see that the m equal to 1 corresponds to a unit step. The m equal to 2 corresponds to what's called a ramp. And the m equal to 3, as we saw before, is a parabola. And I'll let you check these for yourself. We did number m equal to 3 up here at the top.
So, sir, is that parabola, is that 2 factorial or just 2?
Well, okay, let me put it this way. The 2 is there because that is the correct mathematical result.
Because what about if m equals to 4, then that will be 3, right?
That would be a cubic, right?
So now, is it going to be just 3 or 3 factorial?
It's going to be 3 factorial.
So would that 2 be 3 factorial?
Correct. Even though that's not listed here, that would be correct. That is correct. Okay. All right, so I'm at the bottom of page 3. If you got other questions, then I'm going to go to the next page. Or if you got them, ask now. Okay, so if we go back, if we go back to our expression for the from equation 4, right there, and we substitute in our expression from 7, well, then use 7, okay. Okay, this is our anyway, we're going to substitute in, I think some number here got jumped over, but I'm not going to worry about it right now, because it looks like all the logic is there. If we jump over, if we take our last result, which we had, which was our error, up here at the top, that one right there, and we plug in our expression for GC G of S. And we plug in for the R of S, A over S to the M. Okay, so all we did was we pretty much just plugged it in here and here. I think you can see this is what comes out. Okay, just by plugging it in. Now, as it appears, this is not our final result that we're interested in. We're interested in the steady state condition specifically. So we know that means in terms of our procedure to get that steady state result would be to follow this final value theorem recipe, which means we would be multiplying by S, the E of S, and then take the limit that S goes to 0. So let's take a look at that. So if we did that and we wrote that out, in other words, plug in the E of S as we see it here, from here. I think you can see that really nothing mathematically. This is the same as here. So okay, what changed? Well, if you can see, in order to get to there, I had to do one little trick here, which was not intended to confuse anybody, but S over N over S over N. If you can see that. Right, because then if you multiply S over N times S over N, then what happens is you get rid of it there as you multiply through, but you have this 1 times S to the N is S to the N, and then you have S to the N times the A over S to the M, and there's still that pesky factor of S from the final value theorem in there. Any question on that? Okay. Now, as we look at this, we realize that this whole expression is going to be subject to the limit that S goes to 0. But actually, we can take a step to simplify the expression in a way that we need to. And it really does not, change the process or the equivalence of the final result. Is we can say, well, we know that of the two terms here, we can do something which legitimately we can take the limit, and without any confusion on what's going to happen. With the SEN, it's not so obvious for reasons we'll clarify. But anyway, the second term, we can take the limit that S goes to 0 right there and get that done a priori, prior to the final result. And so what we're going to do is let this whole second part of the denominator, we're just going to replace it with that second term with its equivalent after taking S going to 0. So now if you take a look, let S go to 0, then that lets the S go to 0 here and here. And you essentially get this ratio of the product of you could say, well, that's minus to zeros and that's minus to poles, but we know what those mean. But anyway, the product of those quantities, and we don't have any more S left in there. Okay, it turns out that will help us interpret it the way we need to. Now, I'm not sure any one of us would have guessed to do that in the process, but this is, it does seem to work out nicely, and it's described in the book. All right, so we can then, bear in mind, then what we've done is replace this expression which has an S in it with this expression in the denominator that does not. But presumably we're confident it's all okay because we were going to let S go to 0 anyway. Now we can simplify this notice that in another way, we can combine the factors of S that are still outstanding. Since we've got an S to the N, and then we got a 1 over S to the M, maybe to no surprise, you could write that part as S to the N minus M, but then we still have this pesky factor of S out front, and that's what accounts for the +1. I'm not hearing a question. Any questions out there so far? Now, you might notice that this expression, for our purposes of where we need to go, actually encompasses all in one expression, both the information of what type system it is, as well as the type of input we're using. So basically, you find the type information with the N, and the M we know identifies the input. So all of that is compactly represented with that one formula. And now where we're going with this is now we're going to look at some specific cases, and I won't claim it's the only way to do it, but certainly we can't look at all cases at the same section. We have to essentially break them out part by part. So what I have in my notes would be, okay, we first elect to consider what happens when you have a step input, which if we check back, I believe would correspond to M equal to, anybody remember? For a step input, what's the value for M? M equal to 1, right? And we go back, if we forget, we go back here, M equal to 1 for a step input. So then what we'll do is we'll look at these various inputs, and once we pick the input, then we'll see what happens when we change the type for all 3 types. Now the book focuses only on the essentially type 0, type 1, and type 2 systems. Okay, but we could always argue what would happen with the type 4, for example, later. So let's follow the first thing we'll do is take the step input M equal to 1. And then under that category, we'll look at the system input M equal to 1. And then we'll look at the various types of systems with that input. Okay, so if we take M equal to 1, and you can see what's going to happen here. The M only appears in the numerator, but we can simplify this because we got a minus M and plus 1. Therefore, when M is equal to 1, those last two terms go away. And check me on that, but then what you would get would be that expression. Now notice, once we've selected the value for M, then we can then look and break out the various cases for the different type systems. So this we can apply this as we're going to do for both N equal to 0, N equal to 1, and N equal to 2. We haven't done it yet, but that's where we're going. Any question? Okay, so let's say we take the first case, N equal type 0 system, N equal to 0, and as you know, we've already taken M equal to 1, so we can use this formula. And so if N is equal to 0, then S to 0 is, as you know, 1, and S to 0 is 1, and we get this. Now, if we look at this, we see, well, there's all the S's now are gone. There's no, since if we took n equals 0, there's no more S in this expression. And if we take the limit, we're just going to get the quantity back itself. So now presumably the ratio here is not 0. The A is not 0. You know, basically it's tied to the step input. When I say it's not necessarily a unit step, it could be amplitude A. But anyway, the point is that our step input, and then we would have, so it's not 0, and it would fall under the category of being a finite error. Okay, so we would say, well, this is not gonna be equal to 0, and it's not going to be equal to infinity. So we're kind of looking at a situation where we get a finite error. Remember, I told you there's 3 cases. The best case is if it'd be 0, then after that, finite error, and then the unacceptable case would be infinity.
So you said that the N is the type. What is there anything for, are we calling M anything?
Yeah, M identifies the input signal. And I don't know what you say. We have a name for that. I don't remember seeing a name identified with it. So basically, it's just a parameter that identifies the input signal. So you could say, well, the various possibilities are like the step, the ramp, and the parabola, and from which you would know the M, or you could get the M. I understand your question, but as far as I can tell, we don't have a name for it.
Yeah, that was good.
I mean, so now at this point, we'd say, okay, we've identified the fact that, okay, here's a case where we actually did get a steady state error, and it fell in that in-between ground where it's finite. It's not 0, not infinite, but it's finite, and there it is. Now, and you could argue that if you, let's say, for example, you were given the GCG expression, and since n equal to 0, it didn't have it was basically a ratio without the n was 0, so there was no 1 over s or 1 over s squared factors in front. You could in principle work out the zeros and the poles from that expression and then plug that in. And I've actually tried it once, and it does work, but it's a lot of work to do it that way. And it is a much faster way to do it, which really streamlines. In other words, what we're missing here is evaluation of that term. Now, how you evaluate it, I'm claiming you could, in principle, if let's say you've represented this as an n of s over d of s, you could, in principle, factor the numerator and the denominators and come up with a zi and the pk and put those in with presumably there's a k there too. And you could put all that in, and that would not be an incorrect. I've tried it once, it does work, but it's a lot of work, and it takes a lot of more time than this trick. I don't call it a trick or just an observation, but a useful one nonetheless. It actually turns out to be faster and a lot less aggravation to evaluate this term right here. Now, I know that is the term that's important in order to actually numerically evaluate this finite error, because everything else, let's say, you would know automatically in the problem. So the thing is, if you if you would look at GC of S and simply took the limit that S goes to 0, all right, now let's go back a minute and make sure we got the right. So let's look at our GCGS expression. There it is. And take the limit S, and bear in mind that we're looking specifically at the n equal to 0 case. So S to 0 is 1. So we have this here. And if we took the limit, that S goes to 0, by golly, what pops out is exactly what we need here, if you follow me. In other words, rather than all this factoring you have to do to figure out the the zeros and the poles, you don't have to do if all you have if all you do is instead do this limit, okay? And the limit would say just do this limit on the product of GCGS, and whatever that limit when S goes to 0, whatever you get, that can be put in place of that ratio of those factors. Now I realize there is an example coming where we use that, but the point is that I'm hopefully the thread of logic here is at least clear. I'm waiting for a question if you got it. So this thing here in the book, I believe, is called KP, P for position, called the position error constant. And what the rule that we could use here would be, well, we can, let's say, well, the error then would be equal to A over 1 plus KP. And the claim is, based on this argument, the claim is you can get this KP pretty much in a much faster way by doing this limit. And that's really the intended way for you to do it. Any question on that? Okay. All right. So let's go on to so we pretty much, I believe. Oh, there it is. Okay. So to wrap that up here it is. Okay. So this becomes this would be the general form for our steady state error with under the assumptions that the n was equal to 0, right? For the step input. Okay. Now, so we'll go on. That was the type 0 case. Now we'll go on to what's called the type 1 case, where n is equal to 1. Okay, so now remind you that we started with a Swiss knife of formulas for our purposes, this one right here, which covered all possible values for both the type and the m integer for the input. And we already selected the m equal to 1 case for the step input. And that's how we got to this formula on the top of the previous page. So this, again, we need that formula, is my point. And since we got done with n equal to 0, we're now going to do n equal to 1. And that means putting the n equal to 1 there, and putting the n equal to 1 there. And when you do that, of course, it's right here on the page, all that. When you do that, you get this one. Right time to speak up if you got a question so far. Now, I'm trusting when you look at that, you can see that you're taking the limit that s goes to 0, you get 0 plus something finite over 0, which should then become 0 and is 0. Any question? Okay, so we see now a case where with that step input, we've seen in fact that if you up the ante, so to speak, for the type of system, went from type 0 to type 1, all of a sudden with a type 1 system, we see in fact we get the best case. Remember there are 3 cases. We get the best case, and that is 0 steady state error. Okay. Yeah, it could be. I mean, I don't have a sketch for it here, but you could say, well, you know, maybe what here's your input signal, and here's a case where, you know, the response eventually became asymptotically equal to the input. So that basically this, let's say that's your R of t, and this is your Y of t. Okay, and then therefore that error would be the difference between those two, which is 0. Any question on that? Now we're going to find out that in terms of, so we just saw that in fact by upping the ante from a type 0 to type 1, we got an improvement in tracking. We went from finite error to 0 error. And maybe not altogether obvious yet, but we're going to find out as you up the ante in the type of system, it actually tends to track better. So in fact, we're not going to be too surprised maybe when we up it again to n equal to 2, that would be let's see what's, okay, type 2. That looks like a typo. It's not it's a type 2 system, not a parabola input. Okay, so but we're dealing with a type 2 system with a step input. I'm not sure where that came from. Should be step input. We took m equal to 1 in the beginning. There it is, m equal to 1. So the didn't notice that until just now. Okay, so if we evaluate it for a type 2 using the same scheme we did before, here it is, the original result for the m equal to 1, and then we also then proceed to take n equal to 2. We get an s squared there, an s squared there, and again, almost the same kind of argument, s squared in the numerator, s squared plus something finite. Let's take the limit s going to 0, then that should be 0. So again, we see that the, again, we see that in fact, its tracking capability is quite good. Okay, any questions?
I thought that was supposed to be the parabola input.
Well, I think it says parabola, but I'm believing we're in the section, what we're doing is we're going through the different types.
Oh yeah,
a
all 3 of
typo.
these were for the step, right?
Yeah, everything here should be for step. I don't know where the word parabola got in there. I mean, maybe had not enough coffee in the morning or something. I don't know. Anyway, it should be step as I read it again. And I'll fix that in the notes. Okay, so yeah, so what we're doing is we're changing the input and then we're looking at the different steps. So that's now one would argue then for the type 0 case, we in fact saw that there was a finite steady state error. And that was the type 0 case. We found out that there was a finite error. And so maybe that in that particular case, you know, you would expect then that whatever that may be, that we would expect that the y of t doesn't quite converge on the input signal like it did up here. All right, questions? Okay, so we're gonna, and that was the three cases we looked at were for the step input. And so we looked at the n equal to 0, and that was the finite error. N equal to 1, we got the error to be 0, and the n equal to 2, the steady state error was also 0. All right, well, I'm not hearing a question. I'm going to go on to the next case. Here's a summary on the top of this page. And it's intended to drive home the point that the higher type systems are known to be track better.
It looks like we're actually out of time.
Excuse me?
It looks like we're out of time for this class.
What, are we out of time or? Oh, we're out of time.
Yeah.
Okay, that's fine. All right, sorry. Thanks for letting me know. If you don't stop me, I'll just keep going. All right, well then that's it. And I can be here for a few minutes if you have questions, but I'll stop presenting the material. We'll pick up next time with the ramp m equal to 2 case. Okay, so class is over, but if you have a few questions after class, I can leave the Zoom on for a while. Otherwise, I'm going to close the meeting down. All right, not hearing any questions. All right, I'm going to stop in the meeting.